It turns out that most of the functions that we're going to study in this class happen to be continuous wherever they are defined. So these functions include polynomials, so that's your x squared, your x cubed, things of that sort. Exponentials, so e to the x, 5 to the x, 10 to the x, sine and cosine. Additionally, functions that are created by adding, multiplying, or composing continuous functions are also continuous. So that's really helpful because if we can figure out where these types of functions are defined, that will also tell us where they're continuous. And we talked about where they are defined by talking about domain in the first section that we studied. So for example, on what intervals are the following functions continuous? So the first one is sine of x. So if we can consider where it's defined, then we'll know where it's continuous. So sine of x is going to be defined for all x values. All real numbers can be plugged into sine x without any problems. That's the domain. Therefore, it's also going to be continuous for all real numbers. So from negative infinity to infinity, sine of x is continuous. Similarly, x squared plus 1 is defined for all numbers. The domain here is all real numbers. Therefore, it's continuous for all real numbers and continuous from negative infinity to infinity. The third one, the natural log of x, that wasn't on our list. However, it's also a function that's continuous where it's defined. So we have to think very carefully about where the natural log of x is defined. If you don't know, it's worth it to graph it on your calculator and see where you think it's going to exist. But I will tell you, the natural log of x does not exist for negative numbers and is not defined at 0. So the natural log of x is only defined for x values greater than 0. That means it's also continuous only when x is greater than equal to 0. So we can write it like that, or we can stick with our other notation and we can say 0 to infinity. I'm using open brackets again because I'm not including the endpoint of 0. So the natural log of x is only continuous for x values greater than 0. For the next example, we're going to look at something that's not as continuous as other functions we've studied in the past. Instead, it's going to be discrete in nature, and so we have to consider where it's going to be continuous and where it won't be. So consider a pay-by-the-hour parking garage. Any fraction of the first hour is $8. So as soon as you pull in, you're charged $8, and as long as you leave by the 1 hour mark, your fee is $8. However, as soon as you go 1 minute over the 1 hour mark, the price jumps to $16 for the second hour. So minutes 61 through 120, and then $24 for hour 3, and so on and so forth. So it's $8 for each additional hour, but it stays that fee for the entire hour. So if we're talking about the continuity of this function, we have this piecewise function that we can sketch out to see where it's continuous and where it's not. So here, we're going to plot the price versus time in hours. So we can get a good idea of what this is going to look like by graphing what the price is going to be for each increment here. So we know that for the first hour, it's going to be $8 all the way up until the 1 hour mark. But then the price is going to jump to 16 for any amount of time over 1 hour. So we're going to put a hole there because right at the 1 hour mark, it's still $8. And then all the way up to $2. And then all the way up to 2 hours is $16. And then we jump to $24 for 3 hours. And then we're going to jump up to $32 if we stay more than 3 hours. So we have an open circle here, all the way up to 4 hours, and so on and so forth. So this is what's called a step function. It's a piecewise step function. And we can see that we get these discontinuities at the hour marks because that's where we get these jumps, right? And they would just continue going on and on forever and ever. And so we have these small intervals where this function is continuous, but we have a lot of places where it's not. So in terms of where this function is continuous, it's going to be continuous from 0 to 1, not including the 1. It's going to be continuous from 1 to 2, but not including 1 or 2 because we have these jumps. We're going to be continuous from 2 to 3, but not at 2 or 3. And then from 3 to 4, so on and so forth. So on these little intervals between the hour marks, then we're going to be continuous. However, we're not continuous at the integers where we're jumping from either nothing up to 8 or from 8 to 16 because we have these jumps. So we're continuous on the interval, but we're discontinuous at 1, 2, 3, 4, 5. So here again, this is called a step function, and it's an example of a real-world situation where continuity fails for the most part. Okay, so let's talk big picture for a minute. Why is it important to study the continuity of a function? Well, understanding whether or not a function is continuous is important in understanding the variability of a function. We want to know how temperamental it is. How likely is it to change? What sort of impact will it have if I make small changes in what I'm doing? So a function is continuous, such as 2x plus 1, then a small change in the independent variable is likely to produce a small change in the dependent variable. And it's also going to produce a predictable change. So if I were to go from x equals 1 to x equals 1.01, then my continuous function output is going to change from 3 to 3.02. So it's a small and predictable change because it's a continuous function. Now, if you think about the garage and pay example, which was not continuous in general, then a change from 1 to 1.01 results in a huge output change, right? We jumped from $8 to $16, which was a much larger jump. It's considered volatile. We like functions that are continuous because when we study calculus, one of our goals is to be able to use what we know about the function to predict what will happen later. And in order for something to be predictable, we need it to not be hugely variable or volatile. So we mostly study continuous functions, and we try to model with continuous functions in calculus because then we can use it more reliably to make predictions of things moving forward.